Okay, I think we can get started. So just again, the reminder, so if you haven't signed up for the final presentation, please do this as soon as possible. So because, we need the presentation in place. And everything, like the presentation slide, everything has to be submitted on time. So you haven't signed up yet, please go to the sign up sheet to select your presentation date, okay? So for today, we'll talk about adversarial robustness in deep learning, okay? So far we've talked about all the, very good aspect, right, of the deep learning or machine learning, right? So it has been very successful in various applications like image classification, machine translation, and we can using reinforcement learning to perform like the Go game or maybe some other game, right? So we train this reinforcement learning method. So the Google, the AlphaGo, right? So is the first, the AI system that is able to be the human expert in the Go game. And using the reinforcement learning, technology. So all these successful story we've heard in a lot of social media news. But one question we ask is the machine learning is truly ready for the real world deployment, right? So of course you may answer yes. For some applications, it's ready for the real world deployment, right? Because we already have a lot of machine learning service, right? Like the automatic chatbot, right? So recommendation, service, or even the the self-driving cars, right? So we have different levels of autonomous driving, right? So some of the L2 or L3 autonomous driving is already being deployed in this kind of autonomous driving vehicles like Tesla or other automakers, right? So, but again, not all these are perfect, right? We still have a lot of challenges facing, right? So. And there's also, some of the applications, and it has been demonstrated, right? So a lot of machine learning prediction are accurate, but is not very robust. Or in other words, it can be very brittle, right? In some scenarios. So especially we have, kind of a branch of research, or call this kind of malicious attack on the machine learning models, right? So here I list a couple of examples, right? So you hear in these papers or in these studies, they found out that, by meticulously, modify the images, right? Maybe adding noise or, adjust different colors or adding a specific object, a component to the image, in the trained machine learning models can fail, catastrophically, right? So supposedly, you should be predicting like this is a turtle or maybe something or stop sign. By meticulously, right, adding some noise, then the machine learning model can predict, something that is totally different, right? So here's a concrete example, right? So you have this original image, right? So we adding some of the noise, right? We call this adversarial attack, and for a human, right? So even you adding some noise or maybe other, changes to the colors or maybe something else. For a human, right, we can still robustly recognize this is might call image, but for trained neural network, this could be totally misclassified to something else, right? This is classified as a bookcase, right, which is totally nonsense, right? So for a human, we can still recognize this is like the original object in the scene. So we call these adversarial, these perturbed images, or call this adversarial examples, right? So why does this happen, right? So adding small amount of noise or changing some of the pixel values of the original input, why the trained model made such a different prediction? So there are some studies, trying to uncover, right, what's the reason, what's the cause, right? So basically, one of the possible explanation is, for some of the, the input, right? If we add in some of the small noise, because like during the classification, we are, trying to fit a decision boundary, right? So we are trying to fit a decision boundary to classify or separate different classes. And some of the samples, right, maybe lie on very close on the boundary, regions, right? For example, this particular blue, maybe triangle, right? So, or maybe let's just look at this one, the red circle, right? Which is very close to the decision boundary. And if somehow you make small changes to the image, right, the feature can easily cross the boundary, right? Then this can be misclassified to a different class, right? Indicated by this blue triangle. So adversarial examples are these kind of samples, right? So that's maybe very close to the decision boundary, and if you make small changes, then can easily, cross the decision boundary and misclassify to other classes. And here shows some, particular adversarial examples, right? So, some of the examples may not look like a normal image, right? So here, this can be, the neural network, is able to classify these images to like maybe a very high confidence, right? This is a penguin, or this is a starfish, and this is a baseball. Some of them it can be easily understandable, right? So like especially this baseball, right? So as a human, we won't necessarily classify this is a baseball image, right? Because there's no, the specific shape of a baseball, right? But we can understand why the machine learning model classified this as a baseball, right? Because this has the baseball patterns, right? Have these kind of red stitches, right? And also maybe these kind of patterns also, resemblance the starfish, right? Like another example is the remote control, right? So all these kind of like similar to or resemblance the buttons, right, on the remote control. So you kind of, learn some particular patterns, right, to recognize this is a particular class, but not necessarily, right, it's an actual object of that particular class. So, so the adversarial examples here, in the original image, right? So this is, the trained neural network is able to classify this is a panda, right? So once we add in some perturbations, right, basically is the noise we're trying to add, and is able to, make the machine learning model or for the machine learning model, right? In particular, classification model to a wrong class, right? So this is, if we are doing these kind of attack, right? If we want to attack a trained machine learning model, and you will basically trying to manipulate or trying to craft such perturbations or noise, and add this to the original input, so the machine learning model will make a wrong prediction. So here we are talking about the digital attack. Right, so all these are, we are, have a digital copy on the computer. We are adding these digital noise, right? Like maybe Gaussian noise or maybe specific craft noise adding to the digital image, and we make the machine learning model fail. And we can actually do this in the physical world, right? So this is kind of more serious, right? Because, for example, here we have a stop sign right here, and if we can somehow know what kind of patterns maybe make a model, right? So maybe you have a, autonomous driving vehicle, they have this kind of different traffic sign recognition system, right? So here, let's say we figure out a way, right, maybe a particular pattern that can make this kind of, traffic sign recognition system fail. Like you can do like a simple graffiti kind of thing, right? So you paint a specific area, right? So in this example, they paint this like a bluish color, or maybe adding a particular designed sticker, right? Not just a random sticker, but actually specific designed patterns, right? And put that on the stop sign, and when the camera capture this image, right, with this kind of patterns, and feed that into the traffic sign recognition system, and it will totally recognize this is like a maybe speed limit, right, like 50 miles per hour, not necessarily the stop sign. And you can see this can be cause catastrophic result, right? Question.
People have been doing that in real life to like mess up.
Yes, I will later show some specific example, right? Actually, they have a video demo, right? You can actually put something on a T-shirt or wear a specific glass, or even put a paper writing something. Then a YOLO object detector will totally fail. So I will show you example here. So this is actually really serious, right? We can do this kind of physical world adversarial attack to make the model to misclassify. Right. So right, and there's another examples, right? So you in the machine learning in your self-driving car, right? So if this is a stop, at the stop sign, right, as we mentioned before, and maybe you have some physical world attack, the system will thinking this may be a different traffic sign, right? So maybe just a speed limit, or maybe other traffic sign, not necessarily the stop sign. So this will be cause maybe the traffic accident, right? And also this is you can easily think about, right? If we have certain adversarial attack in the healthcare or medical domain, and this is also going to be really cause serious problem, right? So what if some attacker is able to hack into the healthcare system, right? If there's an AI or machine learning model has been used in the AI healthcare system, right? Maybe read the radiology, images, right? X-ray report or something else, right? So they can make the wrong diagnosis, right? If there's any tumor in the patient, right? The model maybe, kind of bypass that, right? To if the model has been attacked. So actually here is an example we can maybe take a look. Okay. So this one, this algorithm is able to inject some of the malicious nodules, right? So to make the AI model to misdiagnosis. And it's also able to remove some of the cancerous growth regions, right? So in this case, then, if this kind of images has been fed into the AI model, it will, will kind of miss the detection, right, of the tumor, and the patient will get the necessary treatment. Okay, so yes, question.
Have there been any records of such attacks being used in the wild to alter medical records?
I'm not sure if there's any reports. It has been released to the media. The hospitals, all these healthcare, they have specific regulations, right? So they may not necessarily release this kind of news to the public, right? Because this may cause panic, right? Problems or lawsuit. So, yeah, but this is the real thing, right? Because, otherwise we wouldn't worry about this, right? So there's a lot of, at least in the research, we have been very successful, is able to generate this kind of adversarial examples to attack different machine learning models. Later, we'll talk about the white box attack and black box attack, right? How this will impact in the real life applications. But to your question, I'm not aware of any reported, but I'm sure there's going to be a lot of cases, this kind of malicious attacker, because a lot of time, people, these kind of cybercrime, they want the ransom, right? So, you can say, okay, I attack your system, right? I'm able to hijack some, personal information, or is able to, remove or modify your healthcare record, and you have to pay the ransom, right? So otherwise, all these information will be released. A lot of time, surprisingly, a lot of these, hospitals or maybe companies, they will actually do that because they cannot afford any of the risk of these sensitive information or being compromised. So that's how these kind of, cybercrime, is kind of so, get out of hand, sometime, yeah. Yeah. So I think that previous example is they are injecting some of the nodules, so the model is able to, because this is not existent in the original scan of the MI or CT, right? But the model is able to injecting these kind of noise, and so that the model is able to detect there are some tumors or abnormal regions. Then the patient has to go through all these different treatment process, right? And the doctor may not even know, right? This imaging has already been tempered, right? Okay. So all these adversarial attack are not necessarily limited to a simple image classification task, right? So we can also do this for other maybe more complex tasks like segmentation, right? So here we can add in these kind of perturbations, right, to the original image. Then if the segmentation model will be changed, right? We're predicting other classes, right? So this is supposed to be a dog class, right? So they will totally predicting other things. And similarly for object detection, right? And not just for the images, right? We can also do this for other type of data, right? So the speech, right? Text, right? So we can, if you're doing the translation or speech recognition, right? So we can add a small perturbation noises to the original audio file. Then some of the speech recognition algorithms will, spit out, totally different things, not necessarily the original, text in the audio. So this is just a high level, right? So how these kind of adversarial attack can make train the machine learning model, very brittle, right? So is able to subject to all kinds of failure. But let's understand, right, how these adversarial attack, is generated, right? So how do they perform this kind of adversarial attack? Once we understand that, then maybe we can come up with some effective solutions trying to defense, right? Because once you understand the attack, we want to do the defense, right? Because a lot of applications, we want to prevent such adversarial attack. So let's just look at an example of the attack, right? So let's using the image classification as an example, right? So let's say we have a trained neural network for image classification. Okay, so this is original input image, right? So which has the ground truth category as cat, right? So it's classified as a tiger cat, and so this XY, X1, X2, and X3 indicating these pixel values, right? So if we form that image into a large vector, and this is the pixel values. So for the adversarial attack, so we're basically trying to add in a small perturbations, right? So call this delta, right? Delta xi. Here, once we are adding this to this image, right? The image maybe look like this. So in this case, I just intentionally make this as noticeable, right? So you're able to notice, right? So this is like a very noisy version, but in reality, a lot of these adversarial attack is trying to deceive the human eyes, right? So make it not perceivable by the humans, right? So you wouldn't tell the image has been tempered or anything has been added to the original input. But just for the demonstration purpose, right? I intentionally make this added noise stronger so that you notice this is an attacked image. Okay. If we feed this into the trainer network again, and it will predicting something else, right? Not the original true class, which is tiger cat. So there's also two types of attack, right? So one we can call this non-target attack, right? So basically, this type of attack is trying to fool this neural network to predicting anything other than the ground truth class, right? Any class other than cat, right? It can be a fish, dog, vehicle, bicycle, whatever, right? Nothing, anything but the cat class, right? We call this non-targeted attack. And sometimes you will also trying to, make the model predict a specific class, right? We call this a targeted attack, right? Not necessarily anything, but I want this to be a specific class, right? A starfish, okay? So maybe, some attacker has some particular, intention, right? Trying to mess up the model, right? Or maybe to his or her benefit, right? Trying to make the model predicting a certain class, like in the healthcare domain, right? So maybe the attacker trying to, specifically target a type of tumor, right? So I'm just making this up, right? So the attacker maybe come from, trying to sell a certain drug or treatment, right? So he or she wants to make the model to predict a certain type, right? So then maybe boost the sale or something. I'm totally making this up just to demonstrate why some people want to have a target attack, okay? So in this case, right, so we want this target class to be, like a starfish class. Okay, so in this case, right, so the original, right, we call this benign image, right? The model is able to predict the original class, right, the tiger cat with a 64% confidence. But after the target attack, right, so the model will predict this is 100%, right, starfish, okay? Of course, you can make other type of target attack class, right, a dog or maybe other class. So, we'll talk about how we can achieve that, right? How you can manipulate the noise so that the model will learn to predict a specific class you specify. Okay. So if we closely look at, right, what are the difference, right? So this is the original input, and this is the attacked image, right? So if we, compute the difference, right, we can, do in the pixel space. At the first glance, right, if I don't do any of these, subtraction, you may not necessarily notice the difference, right? If you just present these two images to you without telling you, one of the image has been tempered or changed, you probably will say, oh, these are two identical images, right? But if we take a close look, right, so we, subtract this image from the other, and even multiply the difference by 50 times, and we visualize these are the differences, right? The pixel differences between these two images. So we even multiply these 50 times, you can observe there's a difference between them. So you can imagine, right, without the multiplication, right, so the differences are, in very, not much noticeable, right? And we can also do this, right, by a different class, right, like this keyboard, and maybe we can also visualize the difference. And the trained network is a ResNet 50, right? So it's a fairly strong or powerful network, right? Not necessarily any of the smaller network that make a false prediction. Actually, a very capable network, but it's just the perturbation, right? The adversarial noise adding to the image make the network make the false prediction. Okay, so here are other examples, right? So, for some, if we are doing this kind of fine-grained classification, right? So for some of the perturbations, right? So we'll make the model to misclassify. But for some of the noises, very strong noises adding to the original images and make this like a fire screen, maybe we can have some certain explanation, right? When the noise is strong enough, right? Maybe this is, the foreground, the background, right? So maybe have some yellow color resemble like a fire, so that maybe make the model predict this is a fire screen. Okay, so let's look at, right, so how we can do this kind of attack, right? So again, let's using this cat image as an example, as we illustrated before, right? So we denote this as the original input, right, x0, and we go through the original trained network, right? Let's say ResNet 50, and it's giving you a high confidence, right? This is a cat image, okay? So this bar is indicating the probability of each of the class, right? So for simplicity, I'll just list these three, high probability class. But the cat is the dominant with the dominant probability, okay? So the label indicating y0, okay? So if we are doing this kind of non-targeted attack, right? And how how this kind of noise, how should we craft this noise X such that, right, the model, the trainer model will make a wrong prediction, any class but the cat class, right? So we're indicating this by Y, okay? So the goal is that we want, the prediction, right, is going to be far away from the ground truth class, okay? So we know that the ground truth class is cat, but in this case, we want the prediction far away from the ground truth, right? Because we want to make the model misclassify its class, right? So here we are indicating this prediction as y hat, right, and the ground truth as y, okay? So we can compute the cross entropy, right? So we can using E as indicating the cross entropy. In this case, right, because we want the model to make the false prediction, in this case, we want to actually maximize the cross entropy, right? Because we want to maximize the distance. So if we were still using the minimization, so we're just adding a minus sign, right? So in this case, we are actually maximize the cross entropy, right, with the ground truth prediction and the actual prediction with the perturbation, okay? So that's the objective for this kind of non-target attack, okay? And another thing we notice is in the optimization is, for the usual, network training, all these things we've discussed before, we are trying to optimize the network parameter, right? So the parameters of the network, okay? But in this case, the network is fixed, right? Because we are not trying to change of an existing machine learning model, right? This machine learning model can be deployed on some company service, right? So we cannot access or change the model. But here, what we are trying to do is trying to manipulate the input, in such a way the model will make the false prediction, right? So here we are trying to optimize or trying to optimize the noise, adding to this original image so that the model will make a false prediction, okay? So that's why we will see in this kind of optimization objective here, we are minimize the loss, right? With regard this input X, right? So what kind of noise adding to this original input X0, the model will make a false prediction, okay? So in this case, we are, you can simply consider now we are, fix this network parameter. We are just changing, the noise, right? How we can find a noise? You can consider the parameter are the pixels of the noise, okay? And this is the loss, right? So the cross entropy, we add a minus sign there. Yes? Question?
Has anyone used this to encode a message in an image? Send a series of images to somebody and then they have to, has noise encoded and then it spits out a message or something, like encryption in a way?
Yeah, the adversarial attack, there's all kinds of ways, right? Depending on how you want to design your, adversarial, patterns, right? So you can, one way is here this example, I'm gonna add in the noise, right? So the information I'm adding is the same size as your original image, right? 512 by 512, but just pixel values adding to, some of the noise adding to each pixel values. But you can also mimic a certain attack patterns as like a watermark, or like you said, right, encryption. I can simply just say, okay, I design a pattern that is mimicking a watermark, right? So like my signature or something like that. But it's not just a simple signature. It's a type of adversarial noise, pattern. In this case, will make the machine learning model to do the false prediction or spitting out any random things that probably wouldn't want. Does that answer your question?
Yeah, but would you be able to control it though, so that it wouldn't spit out something random? It would spit out
specific. Yeah, so that's called the target attack, right? So like, doing the classification is one example. Is I attack the model trying to predict it's not a cat, right? Maybe a starfish or other things. You can also attack a large language model, right? A large language model is supposedly to generate a reasonable, right, text based on the context, your query input or prompt, or maybe an image. But if you attack such large language model or vision language model, it will spell nonsense, right, or even harmful information.
Yeah.
So.
But if you wanted to like send a message to somebody else over, and you wanted to encrypt it, so you could send a series of images with something and with sound, with noise that spits out certain word or something per image, then you could send a message to somebody else. You kind of know what I'm saying. It's almost like you're sending an encrypted message. Instead of using the hashes and all that other stuff, you're just sending a series of images with
Oh, okay. So basically, like, you can sending a random images doesn't make sense, right? A series of images, right? This is a cat, and next maybe a house or something else. And next maybe a cartoon or maybe a word. Then in a way you translate, but you kind of translate it into a meaningful words like sequence.
As long as you have like a certain prompt.
It's a little bit different than here. That can be considered as, like a data encryption, right, kind of thing, because you basically trying to encode a message and converting that in a specific way, right? You want to encode this, and when you do the decoding, then you want to decode a specific image, right? So, the technique may bear some similarity in that sense, but not necessarily, fall into this kind of adversarial attack. Yeah. Yeah. Yes. Question.
I feel that example might be more like security by obscurity.
Yeah.
That like most people wouldn't know that the image can be like encoded in such a way to have a message, but like encryption usually assumes that attackers also have knowledge that this is how you decrypt, this is how you encrypt.
Right.
Is it secure then?
Yeah. So yeah, this is more like in the encryption cyber security, right? So you have a specific code book is able to decode according to this kind of, like a cryptology kind of,
I was just going to say, one example that I've seen in terms of people adding noise to images that aren't necessarily distinguishable from the image itself is I've seen some companies try to do QR codes.
Yes.
So that you can literally just like take your phone, like it looks like a normal picture, like the cat, for example, and then it would register as a QR code, but then to the human eye, you can't really visually distinguish.
Yes, exactly. So like watermark, QR code, all this kind of, to human, we wouldn't raise suspicion, right? So it's like, oh, this is very common. You have watermark or QR code. This is standard things, right? In the social media, maybe QR code is just used for pop-up some of the website, right? But in this case, we can specifically design these QR code very small, or maybe only occupy like a couple of pixels, but the intention is trying to make the model to do the false, prediction, something like that. Yes. Okay, so in this case we are, minimize or trying to maximize, right? So we are the distance between the actually target, the actual prediction and the ground truth, right? So that's why if you have the minimize, we adding the minus sign here. If this is the cross entropy loss. And if we are doing the targeted, attack, right? So in this case, we have a specific target class. I want the model trying to predict, okay? So I have a Y target here. And so in this case, I want the, the actual prediction, right, of this model to be as close as possible to my target class. This target class may not be the ground truth, right? The ground truth is the cat. This target can be the starfish, right, as we see in the previous example. So I want your prediction to be close to my target class. So how do we do this? So actually we have twofold, right, the objective. We want the prediction to be far away from the ground truth, right, which is the cat. At the same time, right, we also want the prediction to be very close to my target class, right, the Y target. So in this case, you basically adding another term, right? So this is, we want to minimize the cross entropy between your prediction and the target class. Although this is a false label for the original input, okay? So this is, basically two loss terms together, and you are able to optimize this objective, so you result in targeted attack, okay? So this is from the optimization point of view, right? So how we can specify these, optimization objective. As I mentioned, right, a lot of these kind of perturbations, right, you adding to the original image, it should be, non-perceivable, right? So otherwise, humans can easily examine, oh, there's some noticeable difference between the images, my original image and this one, right? So then there may be something to this one, then make the model fail, right? So maybe I have to close examine that, right? A lot of this attack is you want to have a stealth mode, right? Nobody will even notice, right? This image has been tempered, and this is just the normal model prediction, right? So basically the goal is that the noise, I don't know why it keeps doing this. Why this is shutting down? Can you guys see the screen? Okay. I cannot control it. Okay. Yeah, but it's just the classroom is really dark right now. Oh, okay. Yeah, I can. Yeah. Okay. So as I mentioned, right, the second objective is we also want the added noise to be very small, right? So people wouldn't even notice there's any difference. So in this case, we want to also have another constraint, right? So the original image x0 and also the perturbed image, right, x, right? So that means after adding the noise to the original image, right, we're resulting in x. Their distance, we'll talk about what kind of distance measure we can consider, right? There should be very close to each other, right? So we will put a specific threshold, right, epsilon here, so that the resulting image wouldn't, perceivable by the human. Okay, so that's another constraint we want to add. Okay, so then how do we define this distance, right? So if we, interpret this as non-perceivable by humans, and the simple way is we can using the L2 norm, right? So basically we can measure the original image and also the perturbed image, right? So from the pixel space, how close are they, right? So we can compute the L2 norm. So basically just adding the square of the difference, right, between each of the pixels, we can compute the distance. And we can also consider this L infinity, right? So this is another distance measure. So this L infinity basically is trying to find which is the maximum of these difference, right? So this x1, x2, this delta is the difference between the pixel value, right? So we want to find the maximum. Okay, so here I want to using a very simple example to kind of illustrate some of the pros and cons of these two distance measures. Okay, and why maybe one is preferred over the other. Okay, so let's just look at a very simple example, right? So we have this 2x2 image, right? So we only have like these 4 pixels. You can change every pixel a little bit, right? Let's say you adding 1/8, right, the value to all these pixels, right, 1/8. And you may result in image like that, look like this, right? So visually you couldn't tell any of the difference because the amount of noise adding to every pixel is really small, right, 1/8, right, or even smaller. Okay, I'm just using a very simple example here. Another way is you can change only 1 pixel, right? I don't know if you can notice this. Can you notice the difference between this one and this one? Look closely.
Red slightly darker, I don't know.
The green is slightly like
The
duller.
green
Yeah, the green one, right? So I'm only adding the pixel value here. So here, I'm adding 1/8 to every pixel, right? Resulting like 1/2 of the change. The other way I can do is I can adding all the value, right, 1/2 to this pixel, and resulting a more noticeable change here. Okay, so in this case, we can compute the L2 norm, and both of the cases, right, can be same, right? So all these can be the same, but not necessarily the number I made up, like 1/8. But adding to small value to every pixel, or adding a fairly large pixel to one value to one pixel, if you're using the L2 norm, cases, you will end up with the same. Okay, but definitely this one is noticeable, right? Then this is not our preferred method. This is actually not our preferred attack, right? Because with the same L2, we prefer this one because this is less noticeable. And this one, you can notice there's a significant change to one area, okay? But if we switch to L infinity, we can actually capture these difference, right? So for this particular example, they have a smaller L infinity, right? Because we are, basically, compute the maximum value added to this pixel, right? So in this case, we have a large L infinity value for this second case, okay? And based on this, like, we can determine, okay, maybe this one is a better choice, right? Because we want this, the distance to be as smaller as possible, right? So this L infinity is actually a better measure in this case as compared to the L2 norm, okay? Okay, so let's just look at how we can optimize this, right? So, before we've talked about how we can construct these loss function, right, in terms of the cross entropy. And at the same time, we have to consider, right, the noise adding to the image should be very small, not perceivable. But let's just forget about these, constraint, right, for a moment. Let's just look at only the loss function here. And so actually, if you take a close examination, right, this is we've been seeing a lot before, right? So basically, optimize the network parameters, right, the weight and the bias. And in this case, we are not updating the weight and the bias of the network parameter because it is fixed, and we are updating the input, right, the x. Okay, so that's the only difference. So, but if you can still treat it as the same way, right? So you can treating this input as a certain set of parameters you're trying to optimize. And to achieve this or to optimize this, we can still using the usual gradient descent algorithm, right? So we can start from the original image, right? And just like you do in network optimization, you may starting from the random initialization or certain type of initialization, right? So as we trying to getting this kind of perturbations, right? And the perturbation is small, we can always starting with the original image, right? And we can do this in an iterative fashion, right? So for the gradient, we are computing this loss with respect to the pixel values, right? So we can compute this partial derivative, regarding to this input, right? X1 and X2, not the weight and the bias, the network parameters anymore, okay? And in this case, we can, this is just the usual gradient descent, right? We have the learning rate, and this is the derivative of the gradient. And we just do this over a certain iterations, and just do the usual, just like the, similar to the network parameter optimization. Now, if we consider another constraint, right, with the distance, and how we can incorporate that in the gradient descent optimization. And turns out it's very simple, right? So basically, we just adding this kind of, you can consider this as a stopping criteria, right? Because we are doing this gradient descent in iterative fashion, right? Maybe from 1 to t iterations or training epochs, right? And we just using this kind of a constraint as a stopping point, right? For each of the iterations, we can measure the distance between the original input and the tth iteration, the image, right, xt here. And if we measure the distance is greater than the threshold epsilon we set here, and we can call it, and we can make it stop, right? So we basically fix this to xt, that's the output, okay? So here is just a visualization. If we are using the L infinity, right? So and we visualize in the 2D space, right? And this is basically how the changes you should make, right? Because we are setting a threshold of epsilon, okay? So you basically, this is the boundary, right? So because this is compute the absolute distance, right? The maximum. So basically in the 2D space, you consider like 2 coordinate, right? The maximum. So this is happen to be, the boundary is gonna be a square, right? So with the distance as the threshold you set, epsilon here. So if anything outside, right, if during the optimization is gonna be outside, if the changes is too large, right, outside these box, and you basically pull it, inside, right, to within this boundary. Okay, so after update, if it's outside the distance, you pull this here so that you can still satisfy this constraint. And of course, there's can be other different constraints, right? But this is just a simple way, to adding a constraint, right? To make the perturbation, less perceivable. And also there could be other, different optimization methods. So here we're just, using this kind of simple way or the common way how we can optimize this, right? Just using the gradient descent. And here we also, explain one kind of attack method, which is only do this in one shot. So that's why they call this fast gradient sign, right? Call this fast one. So because in the usual one, we can do this, in many iterations, but this may take some time. So in this fast gradient sign method, you only do this in once, okay? So you just do this, perturbation one time, and hopefully the resulting image is able to make the machine learning model fail, okay? So for the fast gradient sign method, so basically they adding this kind of sign functions. So for the sign function is basically if any of the value is greater than 0, we consider the output is going to be 1, and otherwise we output a value of -1, right? So this is only give you plus or -1 as the output, okay? So here we are using this as the update, and for the fast gradient sign for this learning rate, and we can simply set this as the epsilon you have, which is the threshold you have, okay? So in this case, you generate the output of your perturbed image. So that's the very simple method to do the attack, and it's only do this one time. Of course, you can expand this fast gradient descent to like a multiple step, right? So you can relax this into like 5 step or 10 step, so that maybe the performance can getting better, right? So the noise adding to the image can be better, and you have a more successful rate to attack the model. Right. So and if this one again, right? So because we have this constraint, right? If this is greater than the threshold, then we can fix this to the boundary, right? So we can take this output actually to the fixed one, right? So we have the boundary as we listed here. Okay, so that's how we can do this kind of adversarial attack, right? So we know the optimization, and we also have some constraint, right? So what kind of noise we want to add, and we can optimize that. And this is based on the assumption that we know the network parameters, right? We know the network parameter theta, and we froze that. Then that's why you can do this kind of back propagation based on the network, and then you optimize the input, right? So this is called the white box attack, right? Because the model is kind of open access to the attacker, right? So you know the parameters of the machine learning model, and you are able to, based on that, to make the optimization. But a lot of times, right, so these models are not open to public, right? So we don't know what kind of model, maybe this API or this company in the service, what kind of model they are using, right? And we have no way to access that knowledge, right? And does this mean, right, if this is the case, if the attacker doesn't know the model, will this be safe, right? You know, or the previous thing we discussed is the white box attack, which means we need the model parameter. But if we don't release the model, you know, to the public, does that mean it's going to be completely safe? The question is no, right? So because we have the black box attack, even though the attacker doesn't know the network parameters, and we can still, you know, trying to have a way to figure out and try to come up with these adversarial examples, trying to make the model fail. And this is how we can do the black box attack, okay? So here we can have a network, right? And the parameter is closed, right? So we don't, you know, the public doesn't have access to it. We don't know the network parameter. And if you have the, you know, if you happen to have the training data of the target network, let's say you may have knowledge about, you know, this company may be using ImageNet to train their model, right? So, and the image happens to be ImageNet is open, this training data is open to public, and in a way, you can come up with a proxy network, right? So the proxy network is basically, you can come up with a network by your own, right? Let's say, I don't know what kind of network that is, but I can come up with my own, right? I can just using the ResNet 50, ResNet 18, or maybe Transformer as a proxy network, right? And because I also know the training data, so I just, you know, trying to make some of the adversarial examples, trying to make my proxy network fail, and hopefully this kind of adversarial example is able to translate to the black box network, right? So that's one way you can do, right? So you can attack this proxy network, and hopefully these, you know, perturbed or adversarial example is going to be successful transfer to this black box network, right? So, but this is not guaranteed, right? Because one adversarial example work for this proxy network may not necessarily work for another network. But later we have some, you know, research showing a lot of cases, right? These kind of attack example is actually transferable. Okay, so if you can make this proxy network fail in some time, or maybe a high chance, some other network will also fail, right? Like if you have happen to have the same family, let's say the black box network is ResNet, 101, but your proxy is a ResNet 15, right? Because they have similar structure or topology, right? Even they have a different depth, but they still may have a high chance for this black box, right, ResNet 101 to be failed. Okay. Another example is, right, so maybe harder cases, what if we don't even know the training data, right? So we don't know the model, we don't know the training data. This is also a lot of time the case, right? The companies will never release, right, what kind of data, because some of the data, maybe they're proprietary data, right? They will never release to the public. So in this case, how do we do this kind of black box attack, right? So in this case, we can maybe, one way is you can query the, company model, right? So you can send, feeding the model a bunch of examples, right? You can, feed a cat, you create a data set, right? You send these images or query the model, and the model will spit out a label, right? And essentially, you can form a label and an image pair, right? And using that as the training data to train a proxy model. Okay, so that's one way, right? You can just query the model and spit out the label, and using that as the training data to train the proxy model. Okay, and to make once you have that kind of data, right, and to make your adversarial more generalizable or robust, you can consider multiple white box model, right? So this can be like the proxy model you can choose, right? You can choose a ResNet 18, ResNet 50, ResNet 101. You can choose a GoogleNet transformer, right? You can list many of these white box model, right? So because they are available, and you're using that as your white box model and trying to come up or train a model to come up with kind of adversarial examples. And in this case, if this example can work for an ensemble of all these white box models, and which means these adversarial example has very generalization capability, right? So hopefully this will also transfer to other black box systems, okay? So that's the strategies, right? So how we can make some transferable or generalizable adversarial examples to do this kind of black box attack. Okay, so here are some of the results, took from this paper, right? So this is the doing this black box attack, right? So the first row are the columns indicating the models to be attacked, which we don't know beforehand, right? So that's why we call it black box attack. So the author did choosing different network as the proxy network, right? So the first one, right, they choose the ResNet 152, right, to be exactly the same, right? This can be happen like just by chance, right? The select proxy is actually the same as the black box attack. You can see that you have a very high success rate, right? This is accuracy, right? The prediction accuracy, right? The 0% means the model completely fail, right? Predict zero accuracy, right? So you have very high successful attack rate. And let's look at, right, so if the proxy is still 152, but the attack model is ResNet 101, the success rate going down, right? Because you still have like 13% accuracy. The success rate going down, but it's still very high, right? You have like majority of the prediction are also false, okay? So these are different cases, right? So some of them perform a higher success rate, and some of them have a low success rate. Okay, so these are switching to different proxy and the corresponding result. Okay, and this is ensemble attack, right? So it's again the first row is the model to be attacked, and the first column indicating we are using all of them together, but minus 152, which is the one trying to be attacked, right? In this case, we only using these four as the proxy, four proxy network to train the adversarial examples. But in this case, you can see that, right? So you can still have a very strong attack rate. In this case, even 100% successful, right? For all these. So this make your adversarial example much generalizable or stronger, right? So you can consider a committee or ensemble of these different proxy networks. Okay, so and also there's papers mentioned there's there existence of a universal like images, and with very small perturbation vector could cause the images to be misclassified with high probability, right? So in other words, you can have a universal attack, a method can make all these different methods fail. So in their paper, they are trying to figure out such universal perturbations. So I won't go to the detail, but if you're interested, you can look into their paper. Okay. Now we can, we want to also share some of the insight, right? So people have also done this attack in the physical world, right? So as I mentioned in the very beginning, right, you can design a specific patterns, right? Like this glass. People wear this glass, right? You can follow the face recognition model, right? So if this person wear this glass and will recognize this is this particular identity, maybe a celebrity, right? The gender even changed, right? So in this case. And this is also, right, the paper they are doing, right? So they change in the sign, maybe adding other stickers, right? So this is the actual stop sign. They put that in their lab, right? So here this called this camouflage graffiti, right? So you can paint some weird pattern on this stop sign to mimic this is some type of graffiti, and people wouldn't notice. And this actually will make this kind of traffic sign model to misclassify this is a stop sign, okay? And here, let's show another example, right? So this is doing the object detection, and you can see that, right? So this is ULO V2, a very early version of the object detector, right? So on the here, right, this person, the model is confidently predict this is a person, right? But if you notice, this person actually put this kind of painting, right? You may consider, oh, this is a very nice painting, right? So doesn't raise any suspicious, right? But you can see that the ULO totally missed the detection. And you can easily put that as like a t-shirt pattern, right? Right? If it's flipped over, right, does not exist this pattern, then it's able to detect. But, right, so if you put it there, the detector is totally missed. Okay, so you can see that, right? This person, hand over this picture to this one. Now, the detector is able to detect him as a person, very, very good, right? Every frame is able to detect, but now this person is missed, right? It's all because of these particular designed, patterns. Okay. Okay, great. So we've talked about all these, detect, right? So now what do we care about is defense, right? Because I'm not trying to teach you to be an attacker, but we want to actually come up, right? So how we can actually defend, right? So here I provide some of the solutions how we can make the model more robust to this adversarial attack. So we'll talk about some passive and proactive defense mechanism. Okay. So for the passive, defense basically means, okay, if we examine some of the malicious attack, then we want to come up with some solution, right? So what we can do is we can actually apply some very simple pre-processing technique, right? So if we know some of the perturbations or adversarial attack is adding some of the noise or pixel value changes, what we can do is how about we just pre-processing, adding some filter, right? Doing some image or signal processing, and hopefully this processing can filter out these kind of harmful noise, right? Then we feed the processed or filtered image to the network, and hopefully it will make the normal prediction, right? So in this case, right, we can apply some of the filters, maybe Gaussian filters, right? Doing some denoising or deblurring, right? Make this noise less harmful. So in this case, the model may still make a correct prediction. Okay, so in this case, right, so after doing the smoothing, right, so this one is adversarial attacked or perturbed image, right? We predict 98% chance this is a keyboard, but if we do some image smoothing, right, apply a Gaussian kernel to do some smoothing, it wouldn't affect a lot of the details, right? Although it maybe make some of the images or edges more smooth, but it wouldn't necessarily distort all these detailed information. But this kind of smoothing will filter out some of the harmful noise, right, adding to the image. So in this case, right, so you can see that it is able to predict this is a tiger cat, right, 37%, right? In this case, even higher percentage, this is a correct class, okay? But they also mentioned there's maybe some side effect, right? So if you have over smoothing, maybe the model you will filter out some of the useful information, then the model may not give a very high confidence of the correct label. Okay, so then besides, we can also do some other filtering or image processing technique, right? So we can do image compression. So hopefully the compression will a lot of time image compression is lossy compression, right? Lossy compression means we remove a lot of the redundancies. Image usually will have some artifacts or distortions. So hopefully this compression will also remove some of the adversarial noises has been added to the original input. Also, we can using GAN, right? A well-trained GAN, right? So you have an input, feeding into the GAN, right? Trying to manipulate the image a little bit, or maybe just using some variation or autoencoder to reconstruct the image. Hopefully, the reconstruction process can get rid of some of the adversarial noise as well, right? So we can using that to feed into the model, okay? We can also do other type of defense, right? Like we can resize the image, right? Only crop out some of the portion. We can pad the image, right? We resize, or maybe do a couple of data augmentation strategies. Hopefully, some of the translations will get rid of some of the noise, right? Make them less impact on the classification model. Okay. We can also, using some proactive defense mechanism, right? So the popular one is called the adversarial training, right? So proactive means we are actively trying to make the model more robust even during the training process, right? So we intentionally, trying to make the model more robust during the training process, right? We are more proactive, trying to make some such defense. Right, so this is the adversarial training, right? So in this case, basically we can make a lot of adversarial examples, right? So here we have, the original, right? We have the X1, right? The label is Y1. So in this case, we can, perform adversarial attack ourselves, right? We can come up a couple of adversarial examples ourselves, and because we generate these adversarial examples, right, we know which image the ground truth label that is, right? So in this case, we can actually put the right label to these adversarial examples, okay? So in this case, we are basically what you are doing data augmentation, right? This data augmentation is basically generate these adversarial examples, but with the correct label, okay? So in this case, the model has been already exposed to the clean image, and also these kind of adversarial perturbed images, but with the correct label information, right? Then we can train this model in a more robust way, okay? So that's the adversarial training strategy, which is widely used if you want to make your model more robust to the adversarial attack, okay? Okay, so here I provide some of the papers or resources, right? So if you are interested in different attack approaches, right? So you can look at these references, and also there's other references, right? So how we can, doing the defense, right? Not just doing the attack, but what other defense mechanism we can consider to make the model is more robust to such attack. Okay. Okay, all right, so that's all for today. Any questions before we end? Okay, great. Then we only have 2 lectures left. I'll dedicate that to the federated learning, which is a private, a distributed machine learning technique. Then after that, we'll starting the project presentation. Okay, I shared a couple of examples, but I will also provide you some guidelines. So hopefully. Maybe next lecture we'll spend maybe 10 minutes. You'll give you like a walkthrough, right? What kind of things you should cover in the final project, okay? Okay, all right, thank you. I'll talk to you next week.
I actually had a question regarding the extension to the question he asked about putting information in images. So we have those QR example that we discussed.